Okay, this is a demonstration of the computation of independent samples t-test. We are going to use a question number 4 from practice computational question. This is in the content, course content and supplemental materials folder, and so uh, you can follow this. Okay, so the data set that we are using is a question number 4. So this is, for example, the question is, I'm interested in examining whether there is any difference in stats exam performance between people attending and not attending TA sessions. Okay, so this is the set data that I copied from this computation, the practice questions. Okay, no attending 76, 80, 79, 82, 85, and 90. And attending is 77, 85, 77, 84, 87, and 91. So given that this group attended, are not attended, this group attended, they are independent from each other. And we are going to, because they are independent, we have to do independent samples t-test. Okay? So the null hypothesis is mu1 is not attending equal mu attending. Okay, there is no difference in the mean between these two conditions. And again, note that we are testing the population mean based on the sample means. Okay. On the other hand, alternative hypothesis is mu not attending is not equal to mu attending. Okay, and we are going to use alpha equal 0.05. And we have to figure out t critical. Okay, the t critical can be found based on the t table here. Okay, so this is in a t table, and in order to get it, you need alpha and also degrees of freedom. So let's say, what's the degrees of freedom? Degrees of freedom is 1, 2, 3, 4, 5, 6 in one condition, 1, 2, 3, 4, 5, 6 in the other condition. Therefore, 6 minus 1 plus 6 minus 1 equal 10, right? So therefore, when you look at this, you gotta look at 10, that's the degrees of freedom, 0.05, that's alpha, so therefore it's 2.228. So therefore, 2.228. This means what we are testing is, okay, so it's non-directional. Therefore, we have in both ends, we have 2.228 positive, negative 2.228. So therefore, in order to reject the null hypothesis, it needs to be either smaller than negative 2.228 or larger than 2.228. Okay? If it's in between negative 2.228 and positive 2.228, we have to retain the null hypothesis. Okay, so let's do, in order to do this, what we are looking for is t observed. That's what we need to compute. Okay? T observed can be given by, in a sense, the generic formula of x1 minus x2. So in this case, non-attending and attending, and divided by standard error. And standard error, in this case, can be computed by standard pooled variance divided by n1 plus pooled variance divided by n2. This n1 means sample size of non-attending, n2 means sample size of attending. Okay, and so in order to do this, you need to get the pooled variance first. Okay, the pooled variance is computed by degrees of freedom 1 minus 1, sorry, n minus 1, that's the degrees of freedom, multiplying variance number 1 plus n2 minus 1 multiplying variance number 2 divided by n1 minus 1 plus n2 minus 1. So essentially what we are doing is weighted average of the variance. So the variance can be computed by using this formula that we've been using to compute standard deviation. So variance equal n sigma x squared minus sigma x, and then entire thing is squared, and n minus 1. So note that variance means it's one step before you take the square root. So you don't have to do the square root. So I'm actually trusting that you can do this because you've been practicing this for a long time up to this point. So I'm not going to actually do the hand computation of the variance for each condition. You should be able to do that using this formula for each of these conditions. So instead of doing that, we are going to use the variance that we've already computed and plug this into this formula. So first, these variance needs to be plugged into this formula of computing fluid variance. So that means, so it's 5, because n minus 1 is 5, multiplying 24.5 plus, because it's variance number 1, 5 multiplying 31.1 divided by 5 plus 5, right? So let's compute this. So this means 5 multiplying 24.5. So 122.5 plus 5 multiplying 31. That's 155 divided by 10. That's, let's do this, 122.5 plus 155 divided by 10, it's 27.75. Okay, so let's check this. Given that this should be the simple average of this and this, because the number of the n are the same across the two groups, so let's test it. 24.5 plus 31.1 divided by 2. Oh, sorry. 24.5 plus 31.1 divided by 2. No, I got it wrong somehow. 24.5 plus 31.1. And then you have to divide it by 2. That's 27.8. So that's the same as 27.75. So given that we got the variance, the pooled variance, now we plug in this 27.75 into this formula. Okay? So this means 27.8 divided by n. This time it should be n. It's not n minus 1. So divided by 6 plus 27.8 divided by 6. So let's compute. And then you have to do the square root at the end. So 27.8 divided by 6 equal. So that means 4.63 plus 4.63 equal. So that means 4.63 multiplying 2. And we have to take the square root of that. That's 3.04. Okay? So 3.04 is, this is the standard error of the mean. Okay? So we plug this into this formula. Sorry, it's getting busy. Into this formula to compute T observed. So this means mean 1 is 8.2. No, 82, sorry. 82. Mean 2 is 83.5 divided by 3.04. 0.04. So 82 minus 83.5, okay, divided by 3.04. Okay, so that's negative 0.49. Okay, so this means where did I get it? Negative 0.49. This is the t observed. So therefore, in terms of this graph here, okay, negative 0.49 is around here. Okay, and definitely this is in the retention area because this is expected. It's a common area. Therefore, we fail to reject the null hypothesis. So we are going to retain the null hypothesis. That is basically the things that you need to do. I'm sorry this gets busy, and hopefully you get the gist of how you should do this.